What's the difference between mobile and desktop processors? I just read about the new Samsung Galaxy Note Edge having a 2.7 GHz quad-core processor and 3GB of RAM. The laptop I bought last year by HP is 4GB of RAM and 2.3 GHz quad-core, and my iMac is even older and is 2.5 GHz i5. Does this mean that the new Samsung gadget is more powerful than my desktop? Is the 2.7 GHz the same kind of GHz as non-mobile devices? Is it scaled up, or compared, etc.? Why, in terms of power, do modern computers not have two of those Samsung quad-core processors running in parallel, pushing out 5.4 GHz processing power for the amount of electrical energy as two Galaxy Note batteries?
Note, this answer is written with the assumption that the CPUs being compared consist of commercially available Intel, AMD, and ARM-based stocks from approximately 2006 to 2015. Any set of comparison measurements will be invalid given a wide enough scope. I wanted to provide a very specific and tangible answer here while also covering the two most widely used types of processor, so I made a bunch of assumptions that may not be valid in the absolutely general case of CPU design. If you have nitpicks, please keep this in mind before you share them. Thanks. Let's get one thing straight. Megahertz, GHz and number of cores are no longer a reliable indicator of the relative performance of any two arbitrary processors. They were dubious numbers at best even in the past, but now that we have mobile devices, they are absolutely terrible indicators. I'll explain where they can be used later in my answer, but for now, let's talk about other factors. Today, the best numbers to consider when comparing processors are thermal design power, TDP, and feature fabrication size, aka fab size, in nanometers, nm. Basically, as the thermal design power increases, the scale of the CPU increases. Think of the scale between a bicycle, a car, a truck, a train, and a C-17 cargo airplane. Higher TDP means larger scale. The megahertz may or may not be higher, but other factors like the complexity of the microarchitecture, the number of cores, the branch predictor's performance, the amount of cache, the number of execution pipelines, etc. all tend to be higher on larger scale processors. Now, as the fab size decreases, the efficiency of the CPU increases. So, if we assume two processors which are designed exactly the same except that one of them is scaled down to 14 nanometers while the other is at 28 nanometers, the 14 nanometers processor will be able to perform at least as fast as the higher fab size CPU. Do so using less power. Do so while dissipating less heat. Do so using a smaller volume in terms of the physical size of the chip. Generally, when companies like Intel and the ARM-based chip manufacturers, Samsung, Qualcomm, etc., decrease fab size, they also tend to ramp up the performance a bit. This puts a hamper on exactly how much power efficiency they can gain, but everyone likes their stuff to run faster, so they design their chips in a balanced way, so that you get some power efficiency gains, and some performance gains. On the other extremes, they could keep the processor exactly as power hungry as the previous generation, but ramp up the performance a lot. Or, they could keep the processor exactly at the same speed as the previous generation, but reduce the power consumption by a lot. The main point to consider is that the current generation of tablet and smartphone CPUs has a TDP around 2 to 4 watts and a fab size of 28 nanometers. A low-end desktop processor from 2012 has a TDP of at least 45 watts and a fab size of 22 nanometers. Even if the tablet system on chip, SoC, were connected to an AC mains power source so it doesn't have to worry about power sipping, to save battery, a quad-core tablet SoC would completely lose every single CPU benchmark to a 2012 low-end Core i3, dual-core processor running at perhaps lower GHz. The reasons? The Core i3/i5/i7 chips are much larger, in terms of number of transistors, physical die area, power consumption, etc., than a tablet chip. Chips that go into desktops care much less about power savings. Software, hardware and firmware combine to severely cut down to performance on mobile SoCs in order to give you long battery life. On desktops, these features are only implemented when they do not significantly impact the top-end performance, and when top-end performance is requested by an application, it can be given consistently. On a mobile processor, they often implement many little tricks to drop frames here and there, etc. in games, for example, which are mostly imperceptible to the eye but save battery life. One neat analogy I just thought of. You could think of a processor's megahertz like the RPMs meter on a vehicle's internal combustion engine. If I rev up my motorcycle's engine to 6,000 revolutions per minute, does that mean it can pull more load than a trained 16-cylinder prime mover at 1,000 revolutions per minute? No, of course not. A prime mover is around 2,000 to 4,000 horsepower, example here, while a motorcycle engine has around 100 to 200 horsepower. Example here of the highest horsepower motorcycle engine ever just topping 200 horsepower. TDP is closer to horsepower than megahertz, but not exactly. A counterexample is when comparing something like a 2014 model Haswell, 4th generation, Intel Core i5 processor to something like a high-end AMD processor. These two CPUs will be close in performance, but the Intel processor will use 50% less energy. Indeed, a 55-watt Core i5 can often outperform a 105-watt AMD piledriver CPU. The primary reason here is that Intel has a much more advanced microarchitecture that has pulled away from AMD in performance since the Core brand started. Intel has also been advancing their fab size much faster than AMD, leaving AMD in the dust. Desktop/laptop processors are somewhat similar in terms of performance, until you get down to tiny Intel tablets, which have similar performance to ARM mobile SoCs due to power constraints. But as long as desktop and full-scale laptop processors continue to innovate year over year, which it seems likely they will, tablet processors will not overtake them. I'll conclude by saying that megahertz and hash of cores are not completely useless metrics. You can use these metrics when you are comparing CPUs which are in the same market segment, smartphone/tablet/laptop/desktop. Are in the same CPU generation, i.e. the numbers are only meaningful if the CPUs are based on the same architecture, which usually means they'd be released around the same time. Have the same fab size and similar or identical TDP. When comparing all of their specs, they differ primarily or solely in the megahertz, clock speed, or number of cores. If these statements are true of any two CPUs, for instance, the Intel Xeon E3-1270 v3 versus the Intel Xeon E3-1275 v3, then comparing them simply by megahertz and or hash of cores can provide you a clue of the difference in performance, but the difference will be much smaller than you expect on most workloads. Here's a little chart I did up in Excel to demonstrate the relative importance of some of the common CPU specs. Note, megahertz actually refers to clock speed, but I was in a hurry. ISA refers to instruction set architecture, i.e. the actual design of the CPU. Note, these numbers are approximate/ballpark figures based on my experience, not any scientific research.
This is a good question. The answer is no, Samsung Galaxy is most likely not as powerful as your desktop PC. And this would be obvious if you would run a comprehensive CPU benchmark test. I will try to put together the answer the way I see it. Other, more experienced members will probably add more details and value later. First of all, due to the difference in CPU architecture, mobile device processors and desktop PC processor support different instruction sets. As you have probably guessed, the instruction set is larger for pieces. Another thing is false advertising. The speed advertised for PC CPU is often achieved and CPU can run at that speed for long periods of time. This is possible because of excessive power supply from the mains, and decent cooling system that allows to remove the heat from the core. This is not the case for mobile devices. Advertised speed is maximal possible speed, but it is much higher than the average speed. Mobile devices will often slow down their CPU because of overheating and to save battery. And the last but not the least is the availability of additional components like main memory, RAM, cache memory, etc. The amount of RAM is not the only criteria. There is also RAM clock speed that defines how quickly can data be stored and retrieved in / from RAM. These parameters also vary between mobile devices and pieces. You could come up with more differences, but the root cause is power consumption and size requirements. Pieces can afford to draw more power from the mains and can also afford to be bigger, so they will always deliver higher processing power. For additional reading, I recommend Processors, Computer versus Mobile.
Actually, megahertz rating has little relevance between different manufacturers' processors. It only has some relevance to CPUs in exactly the same family. While phone processors are becoming pretty fast and might well beat the pants of those old Pentium 4s, you still can't compare them to even a low-end Core i3. You should be aware that there are quite a number of factors that influence overall performance, and not just from the CPU. For example, CPU clock speed, number of processor cores, number of instructions per cycle, branch prediction, instruction set, instruction width, bus width, memory speed. Cache size, cache design, silicon layout, software optimization, etc. So the clock speed or megahertz rating is just one part of a number of different things that you can use to gauge performance. An AMD processor is rather a different kettle of fish than one from Intel or ARM. It's long been known that an AMD CPU at 3 GHz and the same core count does not perform as well as an Intel CPU with the same core count and similar spec and gigahertz rating. And you'll also note that memory speed affects performance too, as well as cache. Noting that server processors have large L1 caches compared to desktop counterparts, and those you'll find in your phone. So they spend less time waiting for data than what a phone CPU might. The reason I've added instruction set and software optimization is that some software can algorithms run better on one chip than another because they can make use of special instructions to speed up certain operations that might otherwise take dozens of instructions. This should not be underestimated. It should be pointed out the TPD has nothing to do with performance. An identical CPU build with a smaller manufacturing process, for example going from 32 to 22 nanometers for example, will result in a lower TDP in the 22 nanometers versus the 32 nanometers die. But has performance decreased? No, quite the opposite. There does exist cross-platform measurements that attempt to gauge relative performance such as the Linpack benchmark. But these are artificial measures and rarely are benchmarks a good indicator of performance for a particular application.
Quixotic's answer gives you the practical side of things very well. I think it'd also be useful to have a short bit on the specifics of a clock is and why all clocks are not created equal. And unless I err, this should hold true across all microprocessors, real or theoretical. 5 GHz means 5 billion cycles or clocks per second. But what happens in a cycle is not represented in the frequency 5 GHz. If a wheel turns 25 times per second, how far does it travel? It depends on the circumference, of course. With a processor, the amount of possible work that can be achieved would be the cycles multiplied by the work per cycle, minus limitations and waiting times. The maximum amount of work done per cycle can be any amount, theoretically. And historically, CPUs have been increasing the amount of work they can do in a cycle. They can do this in a number of ways. When the instruction set size is increased, they are capable of solving a larger variation of problems in a single cycle. More complex instructions allow for solving more complex problems. Logical optimization allow for solving problems with less steps. These optimization have led to and been made possible by adding hardware to the CPU's cores. Certain mathematical operations become more efficient when you have specialized hardware for them. For instance, working with decimal numbers is quite different from working with integers, so modern CPUs have a specialized part of each core to deal with each type of number. Since the cores have become complex, not all parts are used in every cycle, so a recent trend has been to implement some type of hyper-threading that combines two completely separate operations into a single cycle, since both operations mainly use different parts of the core. As you can see, this makes CPU frequency a very poor indicator of performance. This is also why benchmarks are used in almost any comparison between them, since calculating the theoretical performance per cycle is a complicated mess at best. Summary. Since the definition of a core is arbitrary and varies hugely from processor to processor, the amount of work done per cycle of said core is also arbitrary.
Cpuspeed.